Welcome to Conversations That Matter. Today we're having a conversation about climate, one that I've been interested in for quite some time, anxious to have this discussion. And joining me right now is correspondent Mike McNish. Mike, who do we have on today and what's her perspective on climate?
Today, Stuart, it's Dr. Sara Harris. She's an instructor with the Earth, Oceanographic and Atmospheric Sciences Department at UBC. She's a globally renowned scientist on climate change. And in particular, she studies what she calls climate change literacy. In other words, how do all of us, the regular folks out there, learn about and understand climate change, but also take that knowledge and apply it in our own lives.
And I think that is the challenge. Climate is a very complex topic. How do we understand it and how do we understand our role in it?
Yeah, and one of the interesting things that she's doing to help herself understand how we all learn about climate change are called these MOOCs, these massive online classes that many universities around the world are starting, and UBC has started one on climate change literacy. And each semester that they do it, they're getting thousands of people, not just from here in BC, but from all over the world that are participating, learning about climate change, but they're also sharing their own experiences, their own stories about how they're adapting to climate change, how their communities are adapting to climate change. And Dr. Harris is using all that information that she's collecting to help understand just really how are we grappling with this and what is the future portend. She's very critical, of course, as a scientist of the Government of Canada. She says that it's really missing the boat on climate change and points directly to the oil sands as being the fastest growing carbon emissions in Canada. She's very critical of the Government of Canada on oil sands in particular, and even the proposed projects here in British Columbia in particular. She notes, as well as about 25 other scientists who signed an open letter to the public several months ago, that the oil sands are the leading source of carbon emissions in Canada, and that by 2020 there'll be 78% of all carbon growth. And also points to the Trans Mountain project in particular as being a project that has the potential to, by 50%, increase our emissions here in British Columbia alone. She signed a letter with these scientists basically saying we've got to consider carbon and the oil sands when we're looking at these major infrastructure projects going forward. So she's not just a classic sort of researcher in a laboratory, but someone who's really an engaged public intellectual on this issue.
But what's also interesting is that she's hopeful. She believes that we can address this issue and make changes. Fascinating conversation. Let's go to that conversation now. Thank you for joining me to discuss climate. I find it's one of the most interesting topics on so many people's minds today, and yet I think few people really understand what climate is. How do you define what climate is? Because it's different than weather.
That's true. So climate you could think about as long-term averages, okay? And weather is something that is happening short-term. It's about the temperature and precipitation today or tomorrow or maybe up to the next week or so. Climate is like saying, we know pretty certainly that it's going to be colder in January than it is in July, but we wouldn't be able to tell you that it's going to be 10 degrees on January 10th. That's the weather.
Right. So what are the components of the climate? Like what's in the mix?
Yeah. So what really matters is how much energy is in the whole system. So the system has the atmosphere, it has the oceans, it has the plants and the animals on land, it has the rocks too.
It has us.
It has us, yes. We're animals on land. And it really has three components that matter. One is the sun, right? So we have solar energy coming in. One is how much of that energy reflects directly back to space. And then the third is the greenhouse effect and the greenhouse gases, which is the main component that we have direct influence on.
Well, let's talk about the sun, first of all. The sun is the most powerful source of energy. How much does that influence what's happening as far as the climate is concerned?
So the sun's super important, right? That's our main source of energy. What we get from the sun depends on what the sun is putting out and how far away we are, right? So we get more energy from the sun than, say, Mars does, because Mars is farther away, right? So we don't have a lot of control over what's going on with the sun. and it puts out energy. It varies a little bit, right? So what we get varies a little bit as well. And as the sun varies, certainly that's changing the energy coming in.
What about solar flares then? Do they play a role?
So those would be very short-term events. So essentially, no, they would be averaged out into the whole big bunch of solar energy.
I ask because there's a considerable amount of chatter out there right now saying, oh, well, the sun's been more active lately, and that's affecting our climate.
Yeah, okay, so that's an excellent question, right? Is it the sun, right? So one way to look at that is to say, okay, we have observed the temperatures have been going up. Globally, temperatures have gone up. So we have an increasing temperature trend. Let's see what the sun has done over the past century. So what the sun has done since the middle of the 20th century, temperature's gone up, the sun's output has stayed flat.
Stayed flat.
Stayed flat.
Mm-hmm.
So there's variability that goes up and down. You probably know about the sunspot cycle. Mm-hmm. Okay, that's about an 11-year cycle.
Right.
But if we average those out, it's flat. So the sun really has a really nice alibi, right? It can't be responsible for the temperature rise. It should have been going up if it were responsible, and it stayed flat.
Next, we take a look at, like, we've got the atmosphere that we live in. What are the components of that atmosphere?
So the big components are nitrogen gas,
mm-hmm.
which is just N2, which is about 78%, and then oxygen gas, O2,
mm-hmm.
20 or so percent. There's a little bit of argon, that's the third component. And
what
then
exactly is argon?
Argon is a noble gas. It's really doesn't matter in terms of climate. And then there are other trace constituents. So in terms of the greenhouse gases, they are carbon dioxide, methane, and water vapor. Those are the three important ones. There is also nitrous oxide, which comes from agricultural activities. There's also some ozone. There's also chlorofluorocarbons,
mm-hmm.
which are from human activities as well.
So what's the breakdown of them? Like water vapor, I understand, is like the single largest greenhouse gas. Is that correct?
That's true. So water vapor, because there's abundant water on this planet, if the temperature goes up, then water that's available, for example, in the oceans, will evaporate, mm-hmm. and it'll turn into vapor. Right?
Yep.
So water vapor responds really quickly to changes in temperature. I don't know if you noticed last week when it was cold here, it was
mm-hmm.
also really dry.
Yes.
So the water vapor, because the air was cold, the water vapor had condensed out,
mm-hmm.
right? Because it needs to have a certain amount of energy to stay as vapor, and it'll condense into raindrops or snow if it gets too cold. So water vapor goes up and down with temperature. It's very patchy around the Earth, depending on where it's warm mm-hmm. and where water's available. So it ranges from about 0 to 4% of the atmosphere, depending on where you are. On average, this is a bit of a tricky number, but on average you might think of it as about 5,000 parts per million, which would mean that if we could gather together 1 million air molecules, mm-hmm. 5,000 of them would be water vapor.
Can you clarify that for me again? Like, water vapor is what percentage?
So it varies depending on where you are.
Yeah.
Right? So it could be 0 if you're in a desert,
mm-hmm.
right? It could be up to 4% if you say you're in the humid tropics near the ocean. So if we were trying to think of sort of a global average, mm-hmm. trying to average out all the total amount of water vapor, and over time, we'd be looking at something like around 5,000 parts per million.
So that's quite different than some of the things that I've heard about water vapor. You'll
okay.
get some people who will say, oh no, it's the single biggest or largest component of greenhouse gases.
Yeah.
Is it?
So
not if it's only 4 or 5%.
Oh, so in terms of greenhouse warming,
yeah.
water vapor is actually responsible for about 2/3 of the warming. But the key thing about water vapor is it responds to temperature. It doesn't drive temperature. So what's happening is that we, through our activities, are putting greenhouse gases like carbon dioxide and methane in the atmosphere. Mm-hmm. Those are causing the temperature to go up. Water vapor then responds. As I mentioned before, if the temperature goes up, more of the water that's around will go mm-hmm. from the liquid phase into the vapor phase, right? And once it's in the atmosphere in the vapor phase, it's acting as a greenhouse gas, right? So now it's a greenhouse gas. Now there's even more greenhouse gas in the atmosphere, mm-hmm. making the temperature go up even more, helping more water evaporates, making the temperature go up, etc.
When that water evaporates, especially out of the oceans,
yeah.
is it not also releasing CO2? Because I hear that the oceans are the biggest sort of CO2 sink in the world. Is that correct?
So water evaporating out of the oceans does not release CO2. That's just, water evaporating out of the oceans is just taking H2O molecules from liquid to vapor.
Ah,
Yeah.
okay. Because I've heard a number of people go, oh no, that's what happens. When the temperature goes up, CO2 gets released out of ice and out of the oceans and all these different carbon sinks, as I guess they're called.
Okay.
And they go, a CO2 increase is as a result of temperature increase, the same way that you're talking about water vapor.
Okay.
You're saying that's not the case.
Oh, okay. So those are two different things, right?
Okay.
So just like if you had a glass of soda, fizzy, it's cold, and you had another glass of soda, it's fizzy, that's warm, right? And you set them side by side. The one that's warm is going to go flat quicker than the one that's cold.
Because it's going to release the gas.
It's going to release the gas. That's true. So yes, as the oceans warm, they can release gas. What's happening right now, however, are the oceans are taking up carbon dioxide because the concentration of carbon dioxide is going up. So between the atmosphere and the ocean, there's an equilibrium that's being attempted, right? And so at the moment, what's happening is more carbon dioxide is being taken up by the ocean than is coming out.
Does that mean that the oceans are cooling?
No,
For
the
them to
oceans
be
are,
able to draw the CO2 in? I'm asking these questions because I hear people throw this around all the time, saying, well, the oceans are warming up, and so therefore the CO2 is being released. How then does it absorb CO2 if it's not cooling?
So I think you're talking about maybe the boundary of saturation, right? So if the oceans were saturated with carbon, right, then we would have carbon coming out where it's warming. Really, it depends on what's happening in a particular location, right? Some places we have CO2-rich waters coming from deep in the ocean coming up to the surface. In those kinds of places, when they get to the boundary with the atmosphere, they do release CO2 to the atmosphere. And some of those are also actually cold water. But that depends on the relative pressures of CO2 in the overlying atmosphere and the relative pressure in the water. So although in our case of soda, yes, the warmer soda is going to lose its gas, and yes, the colder soda is going to retain its gas for longer. There are lots of little balances that happen. Right now, the ocean on average is taking up CO2. That's actually causing the water to get more acidic, and that's causing problems for organisms that build shells, which will dissolve more readily in more acidic water.
Is it true that algae blooms increase in a more, I guess, CO2-rich environment in the water?
So carbon dioxide is not usually the limiting factor in algae growth. Typically, the limiting factor is going to be light, or it's going to be nutrients. So, for example, we'll get algae blooms in places where we've got sewage outflow, for example. So we're adding a lot of nutrients to the water. We get algae blooms around here in the summertime when it's warm and nutrient rich and there's lots of light around. But carbon dioxide is not usually the limiting factor.
So it's my understanding at the moment we're at about 300 parts per million.
400.
We're at 400.
CO2, yeah.
CO2.
400 parts per million CO2.
Up from about 150 parts 50, 60 years ago. Is that correct? Is my information correct on that?
No, it's not. So,
okay.
So,
see how much stuff there is out there, and it's like, how on earth do you understand all of this?
Well, you can look at the NOAA data set for CO2.
I find virtually every single one of those reports that gets released, I try to read them, and my eyes glaze over, and I go, I don't get it.
Okay.
Like, it's written in a way that is beyond me.
Okay.
And I think that, and I spend a lot of time trying to understand this, and you can tell by the nature of my questions that you're going, well, not quite.
Okay.
I think the big challenge is how do we, any of us who are not in the position that you're in, try and make sense of this?
I think you probably have to look at where your sources are. Typically, the university websites are really quite good. University of Victoria has a really great little tutorial, Climate 101, from the Pacific Institute for Climate Solutions. Government websites are quite good. So in the United States, the NOAA the National Oceanic and Atmospheric Administration and NASA, both have climate programs, and they have their data readily available to people. They also have made quite an effort to try to put things into lay language. But I agree with you, there's a lot out there, and you have to kind of be discerning about which information you're looking at. Yeah.
So we're at 400 parts per million. As
Right.
I understand, okay, plants benefit from it. It's not harmful to us.
Okay.
As I understand, you can walk under the canopy of trees and have a higher concentration of carbon just by going into a forest. You go into a greenhouse and they pump up the CO2 levels way higher than that. You have some kind of medical condition and they up the CO2 content that you inhale.
Okay.
So from a life on Earth perspective, is CO2 a problem, or is it that we have to look at it as a greenhouse gas and its relationship to climate? I'm trying to understand all of this.
So fundamentally, we need to look at it as a greenhouse gas and its relation to climate. Yeah. One of the things you mentioned is in greenhouses, right? So plants under controlled conditions in greenhouses, yes, they could produce more, they could photosynthesize more when there's more CO2 there, artificially elevated levels of CO2. In the real world, however, there is really not good evidence that higher CO2 in the atmosphere in general is going to increase plant growth, because plants also depend on things like water availability. They also depend on nutrient availability. So just pumping CO2 into the atmosphere in general doesn't mean that plants all over the world are going to be really happy.
Okay.
So because
I hear people talk about that, they
Okay.
go, "Oh, well, it's an aerial fertilizer. Plants love it."
Yeah. Okay. So along with climate change comes changes in precipitation, right? Changes in areas that are going to experience drought, changes in areas that are going to experience flooding. So there will be areas where, say, a forest relies on a certain amount of precipitation every year. Maybe they're not getting that anymore. So regardless of the CO2, if they're not getting the water, then they're not going to be
one of the essential
growing.
ingredients.
Right.
Yeah. Okay. So CO2 gets released into the atmosphere. Does it stay within the troposphere? Does it go into the stratosphere? Like, where does it start to affect and accumulate? I guess the accumulation effect change.
So it's mostly in the troposphere, which is the lower, say, 10 to 15
That
kilometers,
we live in, right?
where we live.
Yeah.
So most of, just because of gravity, air molecules there are more air molecules close to sea level than there are as we go up. This is why climbers on Mount Everest, right, have trouble breathing, right, because there's not as much. The air is thinner up there. So that's the distribution of CO2. Because of the wind patterns, carbon dioxide, it stays in the atmosphere for quite a long time. It gets distributed around the world pretty more or less evenly, right? There are some differences because it's a little bit hard to mix across between the northern and southern hemispheres, but it gets mixed quite readily. It also stays in the atmosphere for a long time.
CO2 does.
CO2 does. So some of the CO2 we're emitting today will be around for hundreds of years. Some of it will be around for thousands of years. So you could contrast that to water vapor, which has a really quick trip through the atmosphere. It evaporates, and within 2 weeks, it's back out again.
As rain or
snow.
Some other precipitation.
So if the temperature today were to plunge, for some reason, by 10 degrees, water vapor would just come right out of the atmosphere. CO2 would stay, right? Because it doesn't respond to temperature the same way water vapor does. So with CO2, we're kind of in for the long haul unless we figure out a way to start sucking it back out.
So what exactly is the effect that CO2 has on temperature then?
Okay, so the Earth emits energy. Okay, just if you're not a climate scientist, most people don't think about the Earth emitting energy. But you and I are sitting here, we're emitting energy, we're emitting heat, right? And this table is emitting energy. So the Earth is emitting energy, it's emitting it upward. A greenhouse gas is one that can absorb the type of energy that's coming up from Earth's surface.
So it can hold on to it.
Well, it absorbs it, and then what it does is it gives it off again. And when it gives it off, the energy goes in some random direction. The gas molecule doesn't have any control over what direction it emits this energy. So some of the energy goes back down, it gets reabsorbed by Earth's surface, that raises the temperature of
Mm-hmm.
Earth, right? Some of it goes up to outer space, escapes,
Gone, yeah.
right? Some of it goes sideways and gets absorbed by another greenhouse gas molecule,
Yeah.
which emits it again in some random direction,
Mm-hmm.
right? So there's this constant exchange of energy going on. Sometimes I think about it as this sort of massive water balloon fight, right?
Yeah.
And so what those greenhouse gases are doing is they're essentially slowing the passage of energy from Earth's surface to space. And by the fact that they're emitting some of that downward, the whole surface and the atmosphere warm up.
Okay. Now we need those greenhouse gases for Earth to be habitable.
Absolutely.
Like without them, we're in trouble.
It's pretty cold. It's like
Yeah.
winter in Winnipeg.
Why is it that CO2 has become like the tipping point? Why isn't it methane? I understand methane is a more dense greenhouse gas.
So CO2, one of the main reasons about CO2 versus methane is the longevity of CO2 in the atmosphere. So it lasts a long time. Methane has an atmospheric lifetime of about a decade. So what happens to it, though, is it oxidizes to CO2, which then sticks around for a long time.
Methane changes to CO2.
Right. So the carbon in methane then combines with some O2 and becomes CO2. So methane, for its short atmospheric lifetime, is a powerful greenhouse gas. Then it oxidizes to carbon dioxide.
Okay, so what is the proportion of greenhouse gases when we talked about water vapor? What is CO2?
For CO2, it's 400 parts per million, meaning that if we could gather 1 million air molecules together and find out what they all are, 400 of them would be carbon dioxide.
And so water vapor would be how many then?
If we try to average in time and space, estimates are around 5,000.
So how does this all come together and create a situation where we as human beings become the single most important component in changing the way that the climate interacts with itself?
Yeah, so you mentioned some numbers earlier. So we're now at 400 parts per million CO2. That's a lot higher than we've seen in the geologic record for a long time, right? And the rate at which that is going up is really fast compared to anything we've seen in the geologic record for a long time.